simplest cases when we have circuits with only independent sources, and how can we implement Thevenin equivalent circuits. So the Thevenin equivalent source is computed as the open loop voltage. The Thevenin equivalent resistance can be computed by setting zero all the sources inside that circuit, then determining the resistance seen from the terminals where the equivalent will be placed. Yeah, so basically similar like the previous example in the previous slide. Let's see this simple circuit example. So we have a voltage source here in series with R1, and then an independent current source in parallel with R2, which is then connected to part B in the terminal A and B. Okay, so we have two sources here. To check the RTH, the equivalent Thevenin resistance, we can short circuit Vs and open circuit As. Okay, then it becomes R1 in parallel with R2. So RTH is then R1 R2 divided by R1 plus R2. For example, here we have this example. This is the connected to part B. So here, when we open circuit this part and short circuit this part, then the equivalent circuit becomes, this is 1 kilo ohm, 2 kilo ohm. So this is disconnected, yeah, short circuit, open circuit, and this is short circuit. This is 6 kilo ohm, 6 kilo ohm, 2 kilo ohm, 1 kilo ohm. What is the value of the resistance seen from here? So this is equals to, this 2 kilo ohm is in series with 1 kilo ohm, so this becomes 3 kilo ohm, right, in parallel with the 6 kilo ohm. Yeah, so the result will be RTH equals to 3 times 6 divided by 3 plus 6, 18 divided by 9, yeah, or 2 kilo ohm, yeah, it's supposed to be 2 kilo ohm. Why it is 6 kilo ohm? Let's check later. Right? Let's save this first. Okay, then another example like this. Three times 15 divided by 9. Yeah, supposed to be 2 kilo ohm, yeah, the RTH. So here, if we consider in the second example, yeah, the part B is from this part, yeah, from this part. Okay, so we disconnect this part. So from this line to the right becomes part B. Okay, so what will be the equivalent Thevenin resistance of the part A? So from here, this part we make it as short circuit, yeah, make it a 0. So this become a 2 kilo ohm resistor in series with a parallel, an equivalent parallel resistors of 3 kilo ohm and 6 kilo ohm. So 3 and 6 becomes 2 plus 2 becomes 4 kilo ohm, right? Yeah, I think I'm quite sure that this is not 3 kilo ohm, but instead this is 2 kilo ohm, yeah, for this part. Okay, then since the evaluation of the Thevenin equivalent can be very simple, we can add it to our toolkits for the solution of circuits. Okay. Okay, let's try some example. Find the V output here across this 1 kilo ohm resistor following network using Thevenin's theorem. Okay, so basically what we need to do is to find the equivalent Thevenin voltage source and the equivalent Thevenin resistance. So we disconnect the circuit at this part. So this becomes part B, and the remaining left side of the circuit becomes part A. Okay, to find the equivalent Thevenin source, yeah, independent voltage source, then we make the circuit at B to be open circuit, yeah, because VTH basically equals to the VOC, Thevenin equivalent voltage source equals to open circuit voltage. Okay, so from here we obtain. So basically, when we are like this 2 kilo ohm can be neglected. Yeah, so the voltage, since this is not connected, right? The voltage here will be the same as the voltage here, okay? Because there is no connection here. So the voltage here is the same as here. And basically this and this is a voltage divider. So the voltage here equals to 6 kilo ohm divided by 6 kilo ohm plus 6 kilo ohm, or half times 12 volt. So VOC equals to 6 volt. Then the equivalent Thevenin resistance is calculated by first making all the independent sources in the part A circuit to be zero. So since we have only independent voltage source, we short circuit that independent voltage source here. So that short circuit becomes zero voltage source. So what will be the RTH looking from this terminal? So basically this is a 2 kilo ohm resistor in series with two 6 kilo ohms, which are in parallel to each other. 6K in parallel with 6K becomes 3K, right? 3K in series with 2K becomes 5K. So the Thevenin equivalent resistance is 3 kilo ohm. 5 kilo ohm, yeah, because this becomes 3K, 3K plus 2 is 5 kilo ohm. So then the equivalent Thevenin circuit of this circuit from the left of this terminals are 6 volt, which has then 5 kilo ohm in series with that 6 volt. And these are connected to the 1 kilo ohm resistor. So the output voltage here at 1 kilo ohm resistor can be calculated by using voltage divider formula 1K divided by 1K plus 5K times 6, or 1 volt. Okay, so far is quite clear, yeah, not that difficult. Let's continue with another example. This is more longer circuit with two independent sources. One is an independent voltage source of 12 volt, and another one is an independent current source, 2 milliampere. We are asked to find the voltage output at these two as the 8 kilo ohm. So what we can do is we can cut the circuit here. So this becomes the terminal. Okay. Or otherwise, first cut here. Yeah, replacing this with an independent voltage source, and then we can replace using what we can convert into current source in parallel with this 2 milliampere. In the region shown, one could use source transformation twice, okay? Because this and this can be transformed into current source in parallel with 3K. 3K and then is in parallel with 6K, can be made into a single resistor. Then transform again into a voltage source in series with that equivalent parallel resistor. Then that equivalent parallel resistor is in series with this 2 kilo ohm, etc. Then we can replace them. So reduce that part to a single source with a resistor. Otherwise, we can apply immediately Thevenin equivalent to this part. So RTH is 4 kilo ohm. Where does it come from? So let's try to calculate. So we short circuit this. So this becomes here 2 kilo ohm, 6K and 3K, right? So this is shown in this terminal. So the RTH here equals to 2 kilo ohm in series with 3K parallel 6K. 3K or equal to 2K plus 2K. Okay. Okay. So for the open loop voltage, the part outside the region is eliminated. The VTH, the voltage, the equivalent independent Thevenin voltage will be equal. So open loop, right? This is short circuited. Oh, sorry, open circuit. So it will be a voltage divider, 6 divided by 6 plus 3, yeah, or 2/3 times 12 volt equals to 8 volt. So this original circuit becomes now simplified into 8 volt Thevenin equivalent source in series with the 4 kilo ohm. And basically this we can transform into a current source, yeah, in parallel with the 4 kilo ohm source. Or otherwise we can apply Thevenin one more time with the 2 milliampere source. Okay, the Thevenin resistor here is 4 kilo ohm from the first Thevenin value. Open loop voltage here using KVL. Okay, so the VTH VT1 is 4 kilo ohm multiplied by 2 milliampere. The current is 2 milliampere and plus 8 volt. Yeah. Because this is when the circuit, now the second Thevenin is like this. Yeah? This is 2 milliampere. This is the open circuit VOC here. So this VOC equals to 8 volt plus the current flowing through this part. Yeah? And this is here, so it means plus 4K times 2 milliampere. Okay, so this is because current flowing through here, so the voltage here is why the sign is positive, yeah, according to the passive sign convention. 4K times 2 milliampere plus 8 volts equals to 16 volts. So the VOC is here is 16 volt. This becomes the Thevenin equivalent voltage source for the second Thevenin circuit. Okay, let's save it. Then we have a simple voltage divider, a 16 volt in with the 4 kilo ohm, and then 4 kilo ohm, and then 8 kilo ohm. So the voltage output equals to 8 kilo divided by 8K plus 4K plus 4K, okay, or half times 16 volt equals to 8 volt. Okay, so I hope it can be understood well. We can also use Thevenin only once to get a voltage divider here. So our Thevenin is the part A we extend to the right part. Okay, so the part B only the 8 kilo ohm. So while the left part becomes the part A. So Thevenin resistance is calculated first. Yeah, the equivalent resistance of the left part seen from this terminal. Yeah, by short circuiting the voltage source, independent voltage source, and open circuiting the independent current source. This become here 3 kilo ohm in parallel with 6K, then in series with 2K, which is also then further in series with 4K. Okay, so the RTH equals to this and this 2K, 2 plus 2 plus 4 is 8 kilo ohm, right? Then the independent voltage, Thevenin voltage source, we have to analyze the circuit. So we open circuit this part, yeah, VOC, to calculate the VOC here. And here you can use either nodal analysis or loop analysis, or you can also use source superposition that we have learned last week. Okay, so if we use source superposition, for example, the VOC here first due to the contribution of the voltage source, so means This 2 milliampere is being open circuited, right? So the voltage here equals, if it is open circuit, then equals to the voltage here. Okay, because there is no current flowing from here, the voltage here equals to the voltage here. 6K divided by 3K plus 6K, or 2/3 times 12 volt, equals to 8 volt. The VOC due to the contribution of the voltage source. Then VOC due to the contribution of the current source is calculated by short circuiting the 12 volt source. Okay, and then that will be, if it is short circuit, the voltage equals to 2K plus 2K times 2 milliampere. So whenever you are in doubt, you can always redraw it. So this is 63K. This is in parallel, 2K. Okay, so the question is this VOC due to this, yeah. So basically it's the same as the voltage across this. There's no current flowing here. And this whole resistor becomes 3 and 6K becomes 2K, 2K plus 2K is 4K, right? So this becomes 4K in connecting with this current source. So the voltage here equals to the voltage here, okay? So basically the voltage here equals to, and this is 2 milliampere, the current flowing through this 4 kilo ohm resistor times the resistor, right? 2 milliampere times 4 kilo ohm equals to 8 volt. Okay, so I hope everyone understand it. So from here, then the VOC total will be 8 volt plus 8 volt equals to 16 volt in series with the equivalent Thevenin resistor 8 kilo ohm. And then you put the original 8 kilo ohm load or part B circuit. So then the V output can be calculated using voltage divider formula. So this part is the Thevenin equivalent of this part. Okay, this is a simple voltage divider. So the V output here will be equals to 8 volt. Yeah, so we have the same result as the previous way. So the choice of which circuit you want to simplify using Thevenin circuit is up to you. You can immediately draw the left part of the part that being as if you output here. So immediately you want to replace the whole the from that terminal to the left as one single Thevenin circuit, like in this slide, is okay. Or, but of course, as you can see, it takes some time in order that, and you need to be meticulous and careful so that then you don't make mistake. You use this source superposition. Alternatively, you can use the method in the previous slide. First, you calculate the circuit path to the left of the current source. Replace it with Thevenin circuit here, and afterwards, then you replace it again with the second Thevenin circuit. Yeah, from there, then you can have another simple voltage divider. Okay, so this is more straightforward, but maybe more steps. Straightforward in the sense that you do not really need to be too meticulous, yeah, because you only need to calculate 2 or 3 resistors. So it's up to you in which method, but they should produce the same answer, the same results. Okay, then let's go further. Another example, use the Thevenin circuit, Thevenin theorems to compute V output here. Yeah, so this is now a bit more complex. Still, it has only 2 independent sources, 1 voltage sources and 1 current sources. you have the choice on the way to partition the circuit. Make part A as simple as possible. Okay, so that then you will not be too prone to make mistake. Okay, when you make part A simple, you can check it easily. But when you make part A complex, then you, for example, you need to do very complex mesh analysis, loop analysis, and sometimes you are not careful, and then you can easily make mistake. So if we make this one as part B, there are only independent sources. For the Thevenin resistance, we set to 0 all sources and determine the equivalent resistance at this terminal. Okay, at this terminal A and B. So the 2 milliampere is open circuited, 6 volt is short circuited. So this becomes like this. So we have 2 kilo ohm in parallel with 4 kilo ohm. Okay, so that become 8 divided by 6. Yeah, 8 divided by 6 is 1.5 plus 2. 1.5 plus 2 is 3.5. Is it? 2 and 4, what is the result? 2 and 4 is 2 times 4 divided by 2 plus 4, right? Yeah, 8 divided by 10, okay, 0.8 plus 2 kilo ohm. So 2, this is kilo ohm. So 2.8 kilo ohm, more or less, yeah, correct, right? I think 2 times 4, 8 divided by 10. Correct? Please correct me if I make mistake. 8 divided by 10 is 0.8 kilo ohm. Plus 2, okay, 2.8 kilo ohm. Yeah. Why is it like this here? So this is supposed to be wrong. Eh? Supposed to be this one. Okay. Anyway. For the open circuit voltage, then we analyze the part A. Yeah. Part A here. Okay. So we make open circuit here. So we have two loops or two mesh. Then you can use loop analysis. First loop here. So I2 equals to 2 milliampere. And then at the second loop, minus 6 volt plus 4K I1 plus 2K times I1 negative I2 equals to 0. So from here, then you obtain I2, yeah, this is supposed to be I2, equals to 5 over 30 milliampere. Then voltage V open circuit, here after finding I1, can be I2 and I1 can be calculated as 4K times I1 plus 2K times I2. Okay, 4K times I1 is 2 milliampere. 4K times 2 milliampere. Oh yeah. So I2, this is I2 2 milliampere, sorry. And I got mixed up. So I1 equals 530 milliampere. So 4K times 530 milliampere equals 20 over 3 milliampere or volt. So plus 4 volt. So we obtain VOC to be 32 over 3 volt. So then the circuit becomes like this, okay? And this then the voltage output over the 6 kilo ohm can be easily calculated from oh yeah, wait, I made mistake just now. Okay, but now this can be calculated easily using a voltage divider circuit. Why no one reminding me? Yeah? So everyone is sleeping. Shall we have sudden quiz now? So that everyone will be not sleeping.
No, sir.
Yeah, so if I made mistake, you have to remind me, especially in the simple geometry, in simple arithmetic.
Okay, sir.
If you don't remind me, then I will remind you with short, quick quiz, sudden quiz. I have the book. Yeah, I can just pick any question and then ask you the question.
Not
Okay.
ready, sir. Not
That's
ready
why
for
you
quiz.
have to remind me. Otherwise, I don't know whether you are understanding or you are sleeping. Otherwise, yeah.
Okay,
So
sir.
like this one. Now I know why it doesn't seem to be correct. So 4 times 2 is 8 divided by 6, not divided by 10. So this is how many? Uh, 4 over 3, yeah. Then plus 2k plus 2k. So 2k is 6 over 3. So 10 over 3 kilo. Yeah, that's why it is correct. So I didn't get it just now. Okay, then another example here. Use the Thevenin theorem to compute V output here at the 4 kilo ohm resistor. So we have, this is looks simpler than the previous one because the two sources are independent voltage sources. Yeah. So uh, basically we can choose 4 kilo ohm only to be part B, but to make it even simpler, we choose 2 kilo ohm and 4 kilo ohm as part B. So our part A is here, yeah, the 6 volts, 12 volt and 3K and 6K. So yeah, when you are solving this kind of problem, the choice is up to you. Where do you want to divide the circuit? Okay, as part A and part B. Okay, if you make it like this, for example, then you're calculating your Thevenin resistance will be simpler. Also, the voltage, the VTH, the equivalent Thevenin voltage source will be also simpler. But then calculating the output will be not be straightforward because there is a 2 kilo ohm. In the previous example, in this part, we choose this part. You can also choose actually only 4 kilo ohm to be part B. But then calculating the equivalent Thevenin resistance may be a little bit more complex. But either way, as long as you are doing it meticulously, you are careful in calculating it, then you will find the correct solution. So if we choose 2 kilo ohm and 4 kilo ohm to be part B, first finding Thevenin equivalent resistance between these two terminals. Okay, we short circuit the 12 volt and the 6 volt. Okay. So it is simple, right? It is basically a 6 kilo ohm resistor in parallel with 3 kilo ohm resistor. So the result is 2 kilo ohm. Then we make short open circuit between these two terminals. Okay. And then we try to find the open circuit here. How can we find it? We can use superposition. So finding the VOC here, contribution by the 6 volt. So we make short circuit in this 12 volt. And then calculating the contribution due to the 12 volt, we short circuit the 6 volt and add them all. Alternatively, we can immediately use loop analysis, right, to find the loop current. And then from there, after finding the current, we can multiply the current with this 3 kilo ohm, then plus this 12 volt, finding the VOC. Here we choose the loop current. So 9 kilo equals to 12 plus 6, 18 volt. Okay, the current is equal to 2 milliampere. So the voltage here will be 6 kilo, okay, negative 12 volt, right? Because this is negative. Or 6 volt minus 12 equals to minus 6 volt. Then this becomes the equivalent Thevenin voltage source here, minus 6 volt. And the equivalent Thevenin resistance is taken from here, 2 kilo ohm. And then we connect back the part B, this part, okay, into that equivalent Thevenin circuit. So this 2 kilo ohm and 4 kilo ohm. From here, then we can calculate the V output easily by using voltage divider formula. 4 kilo divided by 2K plus 2K plus 4K. yeah, which is half times minus 6 volt. So V output equals to minus 3 volt. Okay, so here is we have this the same circuit, okay, but the first one we are asked to compute V output using Norton theorem instead of Thevenin. Okay, so let's make partition here. So this 4K and 2K becomes the part B. So part A is this left part. So from here to find the Thevenin resistance, Norton resistance, basically is same as Thevenin resistance. We open circuit the 2 milliampere and we short circuit the 12 volt. So the Thevenin or Norton equivalent resistance seen from this terminal will be equal to 3 kilo ohm. Then we find the short circuit current. Yes, the Norton current source basically equals to the short circuit current when we short circuit this terminal. Okay, based on that, you know that the current will be equals to 2 milliampere, the same as this one. Yeah, is the I Norton IC equals to 12 volt here divided by 3K negative 2 milliampere. So using Kirchhoff current law, yeah, that's if we are in doubt, of course, you can of course redraw again. But it's being such is this ISC. This is 2 milliampere. This is 3 kilo ohm. This is 12 volt. What is the current here? The current here from Kirchhoff current law at this point will be equals to yeah, this 12 volt, the current here minus 2 milliampere. Yeah, this what is I1 minus 2 milliampere. This is ISC, which is equals to 2 milliampere. Okay, so from there, then we can redraw the circuit again at this left part into the Norton current source. And okay, and the equivalent Norton resistor, which is 3 kilo ohm. Then we reconnect again the part B, 4 kilo ohm and 2 kilo ohm. So from here, we can use current divider formula to calculate current flowing through this branch. Okay, that current is equals to 2 kilo ohm here divided by, so the voltage output will be 2 kilo ohm times this current, and that current is this Rn divided by Rn plus 6K times the IN, the Norton current source. So that will be this is how many, the 3 kilo ohm, right? 3 kilo ohm divided by 3K plus 6K, 1/3 times 2 milliampere, 2 milliampere. So 2 milliampere. So times 2K. So we obtain here 4/3 volt. Let's check again. So the Rn here is 3K. So this is 3K. The IN here is 2 milliampere. Okay. So V output will be 3K divided by 9 or 1/3, right? 1/3 over 2 milliampere. 1/3 over 2 milliampere is 2/3. You see here. Milliampere, 2/3 times 2, 4/3 volt. Yeah, this is the value of the output. Okay, so we can. The second question is basically the same, but only you are asked to calculate the V output using Thevenin's theorem instead of Norton's theorem. So in this case, for example, we choose to select only 2 kilo ohm as the part B, and the left part all will become the part A. The Thevenin equivalent voltage here is calculated from the open circuit, right, of this. So then basically will be the same as the voltage here, which will be equals to 12 volt minus VTH here using Kirchhoff current law, VTH minus nodal analysis, VTH minus 12 divided by 3K plus 2 milliampere equals to 0. So from here, then we obtain VTH, and RTH is calculated by short circuiting 12 volt and open circuiting 2 milliampere. So basically 3K is in series with 4K or equals to 7K. So the RTH is 7K. The VTH here, how much will be? Let's calculate. So this becomes VTH minus 12 equals to negative 2 times 3 milliampere, 2 milliampere times 3K equals to negative 6 volt, right? VTH equals to 12 negative 6 volt, correct? So this becomes 6 volt, then RTH is 7. Okay. And this is 2K, so V output equals to 2K divided by 2K plus 7K times 6 volt. 2 over 9 times how many? 12 over 9 volt. Yeah, or 4 over 3 volt. And we see here that the result is the same as the previous result calculated using Norton theorems. So you can, if the method is not decided or is not determined in the question, you can choose either using Norton theorem or using Thevenin theorem, and both should produce the same result if you do them carefully, of course. Okay, 4 over 3 volt. Okay, so we still have some time. Find the Thevenin equivalent at A and B here. Okay, at A and B. So we have one voltage source here. We have another current source here. This is resistor R, then this 2R, and the other one is 3R. Okay. So what is the Thevenin equivalent here? So we need to replace all of this into a single Thevenin voltage source and Thevenin equivalent resistor. To calculate the equivalent resistance, so we short circuit this and open circuit this part, yeah, like this. So what we have is this is in series with this one, it become 3R, and this 3R is in parallel with this 3R. Okay, so we obtain how many? 1.5 R, 3 over 2R. Yeah, 1.5 R. So to calculate the equivalent voltage, here the V open circuit, we can use node analysis, we can use loop analysis, or superposition. Yeah. Actually, superposition is maybe easiest here for in my perspective. Here. Let's say now we try to do loop analysis here. So we obtain here I1 equals to IS. Then we have larger loop here, super loop. Okay, because this one is a current source that is shared by two meshes, so it is better to have one super loop engulfing and closing this current source. So then here we obtain negative Vs plus 5R. This one is in series 3 plus 2 plus 1, so becomes 5R. 5R times I1 plus I2, or this one, this loop I1 plus I2, okay, plus then here the other R times I2. We regroup, and but we have also another KVL here, another mesh here. So VTH here equals to negative RI2, negative 2R here times I1 plus I2. Okay. Yeah. So from here, you see here, it is not that easy. So if you are not careful, if you're meticulous, you make mistake easily in the loop. But if you use superposition with only two sources, it's rather easy. Yeah? Either easier than this loop analysis. So when opening the current source here, so the contribution of the VTH here due to the independent voltage source will be equals as a voltage divider. Okay, so equals to a half, yeah, because this is in series, 3R divided by 3R plus 3R, so half of Vs, and the value negative, yeah, because the negative part here is connected to A. Then contribution due to the current source is obtained by short circuiting the voltage source, yeah, like this. So then we obtain, and we want to find this I1. So I1 equals to 5/6 IS, and then we can calculate the I2 also. I2 is 1/6. This is the current diffusion, 1/6 IS. Then VTH here equals to R times I1, negative, yeah, because this is opposite to the sign. Yeah? So we have to assign negative sign here. Negative 2 RI2. So when we obtain half of the RIS. From there, then VTH equals to VTH1 plus VTH2. So then we can change that into equivalent Thevenin source. So this is the same. We have 6 volt here, 2K here, 8K here, 4K, and independent current source here. Find the Thevenin equivalent circuit from terminal A to B. Okay, so all independent sources is made to 0. So we short circuit 6 volt, we open circuit this one, and here basically then how should we look at this? If you are in doubt, you can always redraw it. Yeah. So basically this is one node. This is also a single node. So it means they are all in parallel, yeah. 4K parallel with 2K parallel with 8K, because this is also the same node. Okay. Yeah, here this is the same node. All resistors are in parallel. Okay. So 2K in parallel with 4K in parallel with 8K becomes here 8/7K. So then we compute the equivalent voltage source here. The circuit can be simplified here as so. This is basically parallel, yeah, 2K and 4K made into a single resistor. 2K plus times 4K, 8K divided by 6, 1.5, yeah, 8 divided by 6, no, 1/3, yeah, 4/3. Then this is also can be simplified further. So we can remember source transformation in the beginning of this session today. So this can be transformed into a voltage source in series with this resistor. Yeah, this is okay. This is 6K. So this can be 3 milliampere times. So this 2 parallel 4 equals to how many? 8/6, yeah, or 4/3 times 3 milliampere, yeah, equals to 4. 4, yeah. This is 4 volt. If we change into 4 volt, negative 4 volt, then this is in series with the 8/6 resistor. Okay, then this is in series with the 8K resistor. Then you can basically you can find VTH here across this 8 kilo ohm as a voltage divider for problem. Okay. So the VTH will be equals to 8K divided by 8K plus 8 over 6K times, so here equals to this one is 6 plus 24 over 6. Yeah. Okay, so that will be all for today. Are there any questions? For circuit with independent sources. So to summarize, for circuit with independent sources, basically it is not yet complex. The complexity occurs when you need to decide at which part you want to divide the circuit. And from there, then you would need sometimes to redraw the circuit in order that you can simplify, find the equivalent Thevenin resistance, yeah, as well as to calculate the equivalent open circuit voltage. That will be the complication, a bit more complex, and you need to be careful which technique you want to apply. You can apply anything that you have learned so far, loop analysis, nodal analysis, or otherwise source transformation, as well as superposition. Okay. If there is no more no